All right, let's talk about stoichiometry. Yeah, I know. That word alone can sound a little intimidating, right? But what if I told you it's not some crazy, complicated secret? What if it's actually one of the most powerful and, believe it or not, practical tools in all of chemistry? Today, we're going to break it all down, and I promise by the end of this, you'll see it for what it is: a simple recipe for building the world.
I mean, think about it. Whenever you cook, you follow a recipe. You need a specific amount of flour, a certain number of eggs. It's all about ratios. But what happens when your ingredients are atoms? You can't exactly scoop them out with a measuring cup, can you? So, how do you follow a recipe for atoms? Well, the answer to that question is stoichiometry.
And really, this is the whole idea in a nutshell. To make a simple cheese sandwich, you need 2 slices of bread and 1 slice of cheese. It's a fixed ratio. If you have 10 slices of bread, you know you can only make 5 sandwiches. Well, chemical reactions work the exact same way. They have these strict, non-negotiable recipes that tell you precisely how much of each ingredient you're going to need.
Okay, so let's take that simple idea of a sandwich and level it up to the real science. Welcome to what I like to call chemistry's ultimate recipe book.
So here's the official definition. Stoichiometry is just the calculation of what goes in, the reactants, and what comes out, the products, in a chemical reaction. And you know, the name itself sounds super complicated, but it's really not when you break it down. It just comes from 2 Greek words, stoichion, which means element, and metron, which means measure. It's literally just measuring elements. See? Not so scary?
So, why should you even care about this? Well, for one, it's got some serious predictive power. A drug company uses it to figure out exactly how much of each chemical they need to make a specific dose of medicine. In any kind of manufacturing, it's all about resource management. You use stoichiometry to cut down on waste, which saves a ton of money. And maybe most importantly, it's about safety. Having the wrong mix of chemicals can be incredibly dangerous, and stoichiometry helps prevent that. All right, so if we can't count atoms one by one, how in the world do we measure them? Well, chemists came up with a clever trick. They invented a special counting unit, kind of like how a baker has a dozen. Think of this as the chemist's dozen. And this is the key to absolutely everything that follows. And that special unit is called the mole. And no, I'm not talking about the furry little animal. In chemistry, a mole is just a name for a specific number of things. Could be atoms, could be molecules, you name it. The mole is the single most important bridge we have. It connects that tiny, invisible, microscopic world of atoms to the macroscopic world of grams and liters that we can actually see and weigh in a lab. So, what's the magic number? It's this, Avogadro's number. 6.022 times 10 to the 23rd. And let me tell you, this number is mind-bogglingly huge. Just wow. To put it in perspective, if you had 1 mole of marbles, they would cover the entire surface of the Earth in a layer 50 miles deep. But atoms are so incredibly tiny that we need a number this massive to work with them. Okay, this is probably the #1 spot where people get tripped up, so let's make this super clear. A mole is not the same thing as mass. A mole is a quantity. It tells you how many of something you have. Mass tells you how heavy it is. Think of it this way. A dozen feathers and a dozen bowling balls are both a dozen things, right? But they have totally different weights. It's the exact same idea with moles. So the big question is, how do we actually connect the count of things, the moles, to the weight of things, the grams? That's where molar mass comes in. It's super simple. It's just the weight of 1 single mole of any substance, and its units are grams per mole. This number, which you can figure out using the periodic table, is the ultimate conversion factor. It's how we travel back and forth between the world of counting and the world of weighing. Okay, we've got our special counting unit, the mole. Now we need the recipe itself. So where do we find the instructions that tell us the exact ratios for our chemical reaction? Believe it or not, it's been staring us in the face the whole time. The balanced chemical equation, that is the recipe. It's that simple. All the information, all the ratios, it's all packed right into that equation. Let's take a look at a super famous recipe, making water. See those big numbers out front? The 2 in front of the hydrogen and that invisible 1 in front of the oxygen? Those are called coefficients, and those coefficients tell us the exact mole ratio. So this recipe reads like this. You need 2 moles of hydrogen gas and 1 mole of oxygen gas to make 2 moles of water. That mole-to-mole ratio, that is the absolute heart and soul of every single calculation we're about to do. All right, team, we've got our counting unit, the mole. we've got our recipe, the balanced equation. Now it's time to put it all together. Let's look at the roadmap for getting from what we have to what we want to find. So for the most common kind of a stoichiometry problem, you're usually starting with the mass, or grams of one thing, and you need to find the mass of another. And guess what? The path is almost always these 3 simple steps. Step 1, convert the grams you know into moles. Step 2, use that magic mole ratio from the balanced equation to switch over to the other substance. And step 3, convert the new moles back into grams. Grams to moles to grams. That's the mantra.
Whoa. Okay, this map might look a little crazy at first, but don't worry. The key idea is actually really simple. See how everything flows through the metal, through moles? The mole is the central hub that connects mass, volume, and even the number of particles. For now, we're just focused on that path from mass to moles and back again, but this just shows you how central the mole is to all of chemistry.
All right, enough theory. Theory is great, but let's get our hands dirty with a real example, right? Let's say we have 10 grams of iron 3 chloride. The question is, what mass of sodium hydroxide do we need for it to react completely? Okay, so here's our game plan. We're starting with grams of our first substance, the iron chloride, and we want to get to grams of our second substance, the sodium hydroxide. See how that fits perfectly on our roadmap? We're going to take that grams to moles to grams pathway. Let's do it.
And here we go. Let's crunch the numbers. Step 1, grams to moles. We take our 10 grams of iron chloride and divide by its molar mass to get moles. Boom! Step 2, moles to moles. We use that 3-to-1 ratio straight from our balanced equation to find out how many moles of sodium hydroxide we need. Got it! And finally, step 3, moles to grams. We multiply by the molar mass of sodium hydroxide to get our final answer in grams, which is 7.40 grams. See, it's just following the steps.
So you can see how powerful this is, right? But it's also a process where one tiny mistake at the beginning can throw the whole calculation off. So let's wrap up with some pro tips to make sure you're dodging those common errors and keeping your answers precise. You know, this reminds me of a fantastic quote from the physicist Richard Feynman. He said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." It's a perfect reminder for any kind of science. You have to be diligent, you have to double-check your work, because it's so easy to trick yourself into thinking you did it right.
So before you finish a problem, just run through this mental checklist. Seriously. Number 1, and this is the biggest one, did you remember to balance the equation first? If not, stop. Nothing else will be right. Did you read the mole ratio correctly? Are you accidentally mixing up moles and molar mass? And don't forget your sig figs. These are the little things that make a huge difference. So at the end of the day, stoichiometry isn't just some boring math problem you have to get through in chemistry class. It's so much more than that. It's the recipe book for the entire universe. It tells us how to build new medicines, how to create new materials, and how to understand our world on the most fundamental level. So now that you have the recipe, what will you create?